Okay, in this next video, we're going to introduce transmission lines that end in an open circuit, and then we'll compare those to shorter lines. And in fact, we're going to link those together and see that it's really all the same phenomenon. All right, so let me go back to this diagram of a transmission line with an intrinsic impedance Z0. And at the end of the transmission line, we now have an open circuit. The wires just stop. All right, into that transmission line, we are injecting an input voltage represented as a phasor, and out of that transmission line will come V out, again as a phasor. All right, so let's quickly jot down what happens. This is, I'm going to make a little table here with the voltage and the current as phasors. All right, this will be input. Let's say that the input voltage has a phasor value of 1, in which case the phasor value of the current will be 1 divided by Z0. All right, so now let's consider the voltage that reaches the load. All right, and let's say this transmission line has length D. We're going to take this value 1 and we're going to multiply it by e to the minus j beta d to account for the phase shift that has occurred as that voltage propagated to the load. For the current, it will be the same thing. We're going to take that 1 over Z0 and we're going to multiply it by e to the minus j beta d. All right, both the voltage and phase propagate in the same way because they must scale with each other for any moving wave. All right, now we've got the voltage that is after reflection. And this is an open circuited line, so the reflection coefficient for voltage is positive 1. So immediately after reflection, we're just going to write down the same thing, e to the minus j beta d. However, for the current, the reflection coefficient for an open circuit is negative 1. It's always a negative of whatever it is for voltage. So after reflection, the current will be 1 over Z0 times e to the minus j beta d. All right, now we got to propagate that back to the load. Sorry, back to the input point. So output here, we're going to take this e to the minus j beta d, and we end up multiplying it by another factor of e to the minus j beta d. There's two negative signs that cancel out to make that occur. The first is that the wave is now moving in the positive direction. So this e to the minus j beta d becomes a positive, but d is also changing in negative direction, right? D goes from 0 to a negative number. And so those two negatives cancel. And so we end up with an e to the minus 2j beta d. And for the current, it's minus 1 over Z0 times e to the minus j times 2 beta d. All right. So now we can write out the definition of Zn. Zn equals Vn plus V out. Keep these as phasors. Divided by In plus I out. All right. And let's just write down the definitions here. This will be 1 plus e to the minus 2j beta d divided by 1 over Z0 minus 1 over Z0 times e to the minus 2j beta d. All right, so you can take any value you want of d and plug it in here. And this is for an open transmission line. And if you manipulate this a little bit, you can show that this equals minus j times Z0 times the cotangent of beta d. All right, so this is the input impedance for a open transmission line. Is minus j times the cotangent of beta d. All right, let's plot what that looks like real briefly, and I'm going to go back to the plot that I drew of the shorted transmission line. and we'll plot this on top. So the blue is the shorted line. And now let's draw the open line. I'm going to draw that in green. The open line is a cotangent. So a cotangent starts out as at an infinite value and works its way downwards. But in this case, you see there is a negative value here. So I'm going to copy this down. Minus j z0 cotangent of beta d. Z in for an open line equals minus j times z0 times the cotangent of beta d. This ends up starting out at negative infinity. It works its way down towards 0, crosses 0, and asymptotically goes to infinity over here. Right? This crossing point where the open circuit transmission line with a quarter wavelength, it crosses the 0 ohms point at quarter wavelength. So it does that same flipping that we saw with the shorted transmission line, except it does it at the quarter wavelength point. So what we can see here is that we're basically seeing the same relationship, right? The same evolution with an open transmission line as we did with a short. All we're doing is we're sort of shifting things by a quarter of a wavelength. So with that in mind, let me go back to this diagram. And for an open circuit, right, D equals 0, and an open circuit, you start here. Sorry, that was a short circuit. All right, for D equals 0 and a short circuit, you start over here. This top plot, the top half of this circle is inductive. And the bottom part of this is capacitive. So for an open circuit, you end up starting here at D equals 0, you've got a perfect open circuit. And as you increase length of the transmission line, you're moving this way, right? This is an increase to D. And the same as before, one spin around this circle represents growing the transmission line by exactly half a wavelength, right? So in that sense, a short-circuited load and an open-circuited load are basically the same thing. The only difference is basically the length of the transmission line that gives you one or the other. But they both roll into each other and into inductors and capacitors as well. So let me take a minute here and show you a demonstration with WinTLS, which does do AC transmission lines. All right, so I'm going to set the source to be a sine wave, and I'm going to have everything be perfectly matched. And so let's just see a nice perfectly matched case, in which case we expect this sine wave to reach the load and there'll be no reflections. This is a moving wave, no problem. All right, I'm going to stop this, and now I'm going to set this to be a open circuit. So I'm going to set this value to be really big. All right, and let's simulate this and watch what happens. It's going to take a minute to reach sinusoidal steady state. We need to wait for a reflection to occur. It's got to propagate back to the generator and then get absorbed there with no reflection. But once that happens, this is sinusoidal steady state. Nothing is changing. Everything is oscillating at the same frequency together. All right. Now, what I'm going to do is I'm going to click on this envelope button. All right. And this is going to kind of show you what the pattern is. And let's say you have the ability to walk along this transmission line with a voltmeter in your hand, and you measure the voltmeter in different places, right? You measure the voltage in different places. If you're standing right next to the load, you're going to see a big swing in the voltage back and forth. If you walk backwards by exactly a quarter wavelength, you sit there with a voltmeter and you measure it, you see nothing. You have absolutely no idea that anything is happening. V equals 0 always, right? What you're observing right now is called a standing wave. A standing wave basically means you have a positive going wave and you've got a negative going wave that crisscross each other and essentially cancel each other out. So you've got a wave that's sort of bouncing up and down, but there's no net motion to it because the energy that's going in one direction is being canceled out by the motion going in the other direction. So again, standing wave. To see this mathematically, let me just remind you that if we have a positive going wave, that effectively means E to the positive J beta Z. This would be a negative going wave. If we add that to a positive going wave, E to the minus J beta Z, right, this would be positive going, then this works out to be the same as 2 times cosine of beta Z. And this works out to be the same thing. So remember, this is a phasor, right? The phasor value is going to vary according as a cosine, which means it starts out with double the value when Z equals 0. And it's going to slowly increase, it's going to slowly decrease everywhere else. Now, this value always has the same phase. It's either 0 degrees or 180 degrees, depending on whether its cosine is positive or negative. But the amplitude is what's changing. And that seems to perfectly reflect what we're seeing here. That everywhere you go along the transmission line, everything is oscillating with the same phase. There could be a negative sign on that phase, depending on whether you're standing at this point versus that point, right? They are opposite of each other, but it's only a 0 or 180 degree phase shift that's there. But the intensity, the amplitude of the signal that you're seeing is varying as a function of distance, and it follows a cosine function. All right. And so again, anywhere you stand, you see the same phase, but let's go back to the perfectly matched case. All right, I'm going to click this envelope again. Number one, the amplitude of the signal that you see is the same everywhere. If you walk around with a voltmeter, you see the same RMS voltage everywhere. However, if you have an oscilloscope and you place it in 2 different locations, the sinusoid that you see will have different phases with respect to each other, right? And that's because this is a moving wave, as opposed to 2 crisscrossing waves that effectively cancel each other out. Right, so this is a purely propagating wave, whereas the case of a really big, effectively open circuit, that is a standing wave. Right. Now, while we're here, let me set this to be a short circuit, and let's see what happens in this case. And I'm actually going to open a second copy of WinTLS. You can compare. Make this a sinusoid. We'll have this one have a very large open circuited load. And let's run that. We'll wait till this settles out. That's the definition of sinusoidal steady state, is that all the transients have settled out and they've all been absorbed. All right. Seem to have a very similar characteristic. Let's click on envelope of this one and envelope of the first one. They look exactly the same. The only difference is in the case of a short circuit on the load, you have a null in the voltage. And if you walk away by a quarter wavelength, you have a big swing in the voltage. It's exactly the opposite for an open circuited load. You've got a big swing in the voltage right close to the load, and as you walk a quarter wavelength away, you have no voltage at all. All right, so what we're seeing here is basically a manifestation of the input impedance. All right, and to do that, I'm going to click on current so we can sort of see how those relate to each other. Let me turn off the envelope. Actually, I'm going to turn it on. All right, so let's start by focusing your eyes right on the load point. At the load point, you'll see that the voltage is changing by a lot, but the current is not changing at all. Right, and that makes sense because an open circuit should not allow any current. So there we've got an input impedance that's very high. If we move to the quarter wavelength point, right where my mouse is right now, here we've got no voltage change, but you got the current changing by a big amount. So the current and voltage are also off by 90 degrees with respect to each other. And again, this is the voltage and current that represents the sum of a positive going voltage and current with a negative going voltage and current. Those sum up to create this standing wave pattern, or a bouncing up and down wave that does not seem to be moving. All right, so that concludes lecture part number 3. In the final portion of this video, we're going to talk about general reactive loads where we have inductors or capacitors on the load. And that will turn out to be a pretty straightforward extension of this open and short circuit treatment.